Alright, time for another draftphysics.com, debatephysics.com also, but no one pays any attention. Yeah, there's lots of 5-minute videos on the debatephysics.com, and making these individual specific arguments of how kinetic energy fails, and it's just unfortunate that nobody responds to any of that material in kind with some counter argument. And instead, this is all we get. So anyway, Paul Nord has returned to be fed once more. So that's good. Maybe he'll figure out that is a conversation here worth having, and but maybe not. I don't know. So eventually I'll post this whole insanely long thread of back and forth gibber and jabber, where none of my points are really argued, and I'm certainly not provided the evidence that has them so convinced. I mean, that's what I want to see is, why are you people really convinced it takes 25 times the fuel to spin or move something 5 times as fast? Why are you convinced that that's a plausible truth? And there's just so many experiments. So the last video I made, I was kind of happy with until I thought about it, and I said, wait a minute. So I used the angular momentum theorem, and the problem is the velocity is in radians. So, it's not the actual velocity of the objects, it's the velocity of the angle. And so the angle for the inside mass and the outside mass is the same, twice the speed on the outside is the same velocity in terms of an angular velocity. So it does make it a little confusing. I said, well, I probably should have just stuck with the law of the lever. The distance is the same as the velocity, so we only need one term for that. And the mass is the mass, frankly. And it's just mass times velocity. And those things have to be equal. And it works, and it doesn't need to be any more complicated than that. So anyway, so we'll read the latest by Paul. Not much, frankly. It's just little snarkies, but at least it gives me the opportunity to again just plead. Can't you do better than this? I mean, can't you just engage in the conversation and attempt to deal with the actual reality that is pretty stark in terms of showing paradoxes? But anyway, so I believe this should work. Oh, look at that. All right. So I'm probably going to go through some, some redundancy as because that's all I can do. I mean, until they deal with the conversation and as it's presented, what else can I do? You just keep saying, well, look, it doesn't work for gears, and it doesn't work for levers, and it doesn't work for ballistic pendulums or any kind of inelastic collision. And the elastic ones are under debate in the sense of you're arguing you can make free momentum, which I say is problematic. Yeah, if not, entirely paradoxical. So anyway, he says, okay, I'll bite. So I sent him a video, and I wasn't, he was pretty much hadn't said anything for a couple of days, so I didn't figure any response. I'd just make a final video. So he says, please describe your calculations. So he did this earlier of the ballistic pendulum. And you're like, well, the ballistic pendulum is this simple inelastic collision thing. What's to calculate? I'm claiming it's just silly to think, kinetic energy has anything to do with it because the kinetic energy is lost in dramatic amounts. The simplest experiment, half of it's gone, and the more complex ones, 99.94% of it is gone. No evidence of it, and the idea is if you do it simply, you can conserve all of the momentum, like close to 100%. When you're doing something more challenging, like trying to catch a bullet, well, yeah, you won't be able to get all the momentum back, preserve it or collect it. But you certainly know where it is and the deformation it does create in whatever medium you're using to absorb the bullet's momentum. but no kinetic energy shows up. And there's no point in saying you lose kinetic energy. The simple argument is it was never there in the first place. All the thing has is the momentum, and in no ballistic pendulum do you ever collect enough energy that's more than the momentum. So the momentum says 2, the kinetic energy says 2,000. You see, there's almost no point in talking about, oh, I didn't get all the kinetic energy. No, you didn't get any. All you got was the momentum. All right. So then it says, do you have a paper on this? Again, what, conservation of momentum? I should have a paper. Anyway, perhaps you can write something. Pretend you're turning it in for a lab credit. So, these are just little silly, nonsensical jabs of, of no consequence. They're just so poor and pitiful. So anyway, I'll read my response. Okay, I'll bite. I don't know why that isn't in colored text. Unfortunately, you won't chew on anything. So, he really won't. He'll just play this, whatever this rhetoric game is, but he really won't show us, how the physics really works. Please describe your calculations of the ballistic pendulum. So again, it's just as simple as you can get. You have something with momentum, the two objects combine, and all you're really doing is saying, I'm just going to add the mass of one object to the other object. There's nothing more complicated. And the increase in mass means you have a decrease in velocity, and you conserve the momentum. So it's mv in equals mv out. I mean, So you're almost saying, why would you write this sentence? I mean, there's no calculations for the ballistic pendulum. It's completely uncomplicated. All right. The calculation is consistent with the conventional conservation of momentum model. mv equals mv in equals mv out. Big M, little v, big V, little m, all the same thing. As the ballistic pendulums seldom have opposing directions, well, I mean, they never have opposing directions, frankly, vectors, it's just a matter of accounting for small losses to heat and deformation. So the car example, the cart or the moving object in space, and you double its mass, you combine it with another mass, and now you have a twice as heavy thing going half the velocity. Perfect illustration, frankly. Half the kinetic energy is gone, and all the momentum is conserved. And so what about that argument is obtuse and complicated? I viewed dozens of experiments done various ways, and without exception, most of the kinetic energy is lost, and most of all of the momentum is conserved. Is your experience different? So, see if he answers. If kinetic energy is real, why can't it ever be successfully collected? And that's the argument. It's never used to do work. It can't make it do work. It'll either create heat, they say, or it'll yeah, that's it. There's no other explanation. It just the energy dissipates into some form that in some way is useless, but you can't collect it as momentum. You can't convert the kinetic energy into a momentum equivalent. Let's see, do you have a paper on this? So I said, conservation of momentum isn't new science, but I have started doing some writing regarding the general subject of energy, so that's the stuff I wrote a month or two ago. Just beginning to explain, how the real physics really needs to be a description of the real universe, and the real universe is where the electrons and protons live. They make everything happen. So their interaction with space and the force, that's where everything happens. And I do have a 7 or so minute video that shows and explains my quite perfect simulation of charge. So I linked to the 7-minute video. We'll see if he'll watch it. So a very simple mechanical system creates explains why electrons and protons attract and repel their likes. Explains one of the most basic phenomena in physics that currently remains a mystery to the physicists. All right, so then he says, perhaps you can write something. I mean, just you're just like, so what? Drawing it isn't good enough. I could even, show a video of the experiment itself. That's not good enough. Some written words are going to be the key to the whole thing. I don't think so. Why do you make videos demonstrating it if you think writing is so effective? So his channel's covered with videos that are basically, I mean, they're a little childish, rubber bands around watermelons, karate chopping stuff, to me it's not, these aren't exactly precision experiments. So in most of my videos I am illustrating concepts and diagramming an experiment. The clear challenge is for a dissenter to respond in kind. I mean, that would be just so sensible and reasonable to me, is that if the counter argument was presented in the same form I presented my argument, the same language, the language of a diagram explaining how you think the forces are interacting. Respond in kind with a better diagram and explanation, but that doesn't happen. In my opinion, that's good science. So yeah, I think drawing it, it makes sense. And I think most physicists do understand that. Now there's some physicists who just do math, but they'll try to draw it. Like Feynman would try to draw something now and then. And, they weren't very good drawings, but I'd give it a shot. But then he'll do the double slit pattern as a bunch of just sloppy lines and say that's it. Just cheat horribly. Professor Lewin was pretty articulate in his drawings. He was kind of careful to make circles, and to do things quite nicely, actually. All right, anyway. So then the last line is, pretend you're turning it in for lab credit. And I say, I'm not a big fan of pretend. Why don't you pretend? Why don't you do it first and pretend you're a fair cop for a minute and concede ballistic pendulums aren't very good evidence for the existence of kinetic energy? I mean, that's the least they can do, is just concede, oh yeah, it doesn't look very good. I mean, obviously when you're not collecting 99.94% of something, yeah, that looks pretty bad. In every single case, I can never get more than the momentum. I'm always way short of the kinetic energy, and I'm always pretty close to the momentum. Yeah, it's pretty good evidence, that one is real and one is not so much. But no, they won't concede. They won't concede anything. And it's just so, frankly, from my perspective, I have to say it appears to be insanely dishonest not to make those concessions. And such. All right, so I guess we'll have to draw something relevant to the subject. Well, I'll do the ballistic thing just one more time. Just it's such a simple argument. Then we can do maybe some of the other ones that I've already drawn hundreds of times. Sadly. Alright, so since we're on the subject of the ballistic pendulum, I'll do that real quick and then we can move on to some other stuff. But again, the simple idea is I can have a very small mass with a very high velocity, which means a very high kinetic energy, okay, because of the squared term on the velocity. And I can combine it, okay, have another mass absorb it, or it absorb it, doesn't matter who's absorbing who. But they become one consolidated object, and the consolidated object will only acquire the simple v part. It won't acquire the v squared part. So it's just going to be the new increased mass, okay, and a new smaller velocity. That'll be the outcome. So you have a small m and a big v going in, a high kinetic energy, and you have a very large mass with a small v and very low kinetic energy coming out. And so I would argue that the kinetic energy part basically is worthy of just forgetting about it. It doesn't have anything to do with anything, because all it's going to matter is the mass and the velocity. That's all that's going to take place in the interaction, is the exchange of the momentum, the combining of the momentum. Now, the ones that get more complicated is when you have momentum opposing momentum, and as I've sort of pointed out, the pendulum kind of demonstrates the outcome of the basic experiment. If you collide two balls, okay, with a substantially even amount of energy crashing into each other, if you allow them to reflect, they'll reflect completely. That is, whatever goes in will come back out again. But if you force them, okay, not to be able to rebound and move freely, then all of their energy will be converted into heat. And so that's an experiment that's kind of easily done. You can just take two steel balls and smash them into each other and force them to stay close, and they will basically vibrate back and forth really quickly and create a lot of heat and deformation of any material you put between them. And that's where your momentum will be dissipated, because it has to go somewhere. So there's no such thing as canceling momentum. It never cancels. If you don't see something fly out of a collision, okay, then there's something you're not seeing that is, and that's usually heat. So if you're not seeing anything happening, there's something still happening. Okay, there's never a non-event of motion. And so it's like friction, just taking the energy from something rolling. And again, these arguments, I mean, I guess some people actually think friction is a real force, that somehow, that's really way to hell. That's in a place that just isn't going to work. I have all this room over here. So one of them that has twice the velocity. Okay, so you got one velocity and two velocity, and then you have this rolling thing, and it goes 4 times the distance. And clearly, what's happening is that as the thing rolls, it's losing its momentum to the ground. The ground is absorbing it as motion. The little bits inside the ground are moving. It's still momentum. So heat is still momentum. It's just momentum in all kinds of directions. It hits in a spot and it radiates into a bunch of other atoms and molecules, and they all start jiggling and moving. And so the heat is just momentum in all, being converted back into, say, an explosion, where it's dissipated in all directions and becomes less useful. So you could just argue that all linear momentum is a kind of heat with a specific direction. And that heat without a direction, that's what we call heat. Okay, but everything is heat. Everything is just the motion of these little atoms. The electrons and protons are where it all happens first. And, so obviously in this experiment, the faster you're going, drew it wrong again, the less contact you have with the surface, because the force of gravity is a time-dependent force, and you don't have enough time to weigh your full weight as you're rolling, and so you're not making very good contact. And the slower you go, the more contact you make. So you go half your velocity 3/4 of the way down the track. Now, just a huge giveaway, okay, that you're not losing energy at the same rate, okay, as you roll. And the faster you're moving across the surface, the less pressure you're putting on the surface, the less contact, the less conductivity, the less ability to leak your energy into the surface. It's perfectly logical. It's easy to understand. And then you can tilt that, to make the gravity argument, because it's exactly the same principle. So if you were dropping something, you can understand it'll drop at a certain rate. And it's the same equation. Okay, 1 unit of time looks like this. This will be 1 unit of time. This will be half your velocity. The second unit of time, you'll do this. It's all the same units of time, right? So, I mean, it's the same basic equation. And if I was to think about it as applying friction, that is blowing some force against something as it fell, I could understand that the faster I was going through the wind, there's a wind blowing this way, the faster I fall through the wind, the less the wind can push me into the surface. I mean, it's duh. The faster I go across a stream, the less the stream moves me. I mean, you know, pretty obvious. All right, so let's get to a pressure vessel, because I think that one's the interesting one. And I kind of made a mess of it in one of the other videos. Well, I wouldn't say a mess, but it wasn't as good as I should have done it. So the idea is there's bits of energy inside of something, and they're pushing out. Okay, so I have high pressure. It doesn't matter, air or whatever. And so the molecules have a certain activity. And the catch is they hit the surface. And the fact is they have if the surface yields, okay, just like a brick wall and a ball being thrown at it, if the wall doesn't yield, it's bouncing back. If the wall does yield and moves, then the energy is absorbed. It got, stuck to it and it moved it. So the same thing's happening inside the vessel. So the vessel vibrates, probably. We can't see it, but it's probably jiggling a little bit. And it ends up moving a little bit this way, and then the other side moves a little bit this other way, and they, basically keep moving each other into each other. So at any one moment, the force bit could hit and stick and actually move the surface. But the catch is going to be is that that's going to happen the opposite way on the other side, and something's going to hit and stick there. And so those are going to be competing pieces of energy, and both of them are going to end up reflecting eventually back into the vessel. So it's not as simple as it is as simple as it either sticks or it doesn't. And so the catch is, let's say I open this thing. Let me take some of these little bits out of here so it's easier to see. Why don't I just make it bigger? I could do that too. Okay, it's not rounder, but it's bigger. All right, and so I make a hole. All right, anywhere, and the idea is that some force flies out this way. Now, what does that mean? It means it never hit this surface. So what was keeping things at a balance was the fact that there was the same amount of stuff hitting this way as was hitting this way. And the catch is that there was enough motion this way to force reflections of the other side that way. So everything was forced to reflect. Now that I've let that loose, now there's extra energy this way, in the sense that there's the brother, the clone, okay, the opposite twin of this piece of energy that's now leaving. And now we have this one as an extra. And so now this surface can yield this way, if you get it, right? Because there's no counter pressure. There's going to be missing the part where this surface moves that way because this one hits this surface that way. So that pressure is not going to exist. So the obligation to reflect isn't going to exist. And so now it's going to be an absorption, and it's actually going to move. So now the surface will move with the disproportion. So the more I let out here, the more opposite force I have hitting this other side that's unresponded to. That is, it's not going to be reflected, it's going to be absorbed. And so now it moves, okay, the whole surface can move because there's no counter force hitting the other side. I think that's simple enough. So you're missing all of those arrows going this way hitting this surface. So obviously this surface has more energy hitting it, and therefore it can be absorbed and now move the object because there's not going to be a reflection. And basically that's thrust, and it's completely any direction. There's no plus and minus direction. I could let the force out anywhere I want, and it's going to work just as well, demonstrating that direction doesn't mean anything in terms of I can choose any direction, and there's no penalty for choosing a direction. Alright, so I guess I'll do some of the elemental stuff. So it's my argument that electrons and protons, they do have a character. I mean, they are opposite to each other in character. And the fundamental difference is that if a proton force hits an electron, it comes out an electron force. And if an electron force hits a proton, it comes out a proton force. And that creates a mechanism where these objects end up radiating, only one force. So two forces come in and only one force ever radiates out. And so they become opposite in that sense, and only the electron force can push an electron and only proton force can push a proton. That's why they repel. And because the green force is inert to the red object and the red force is inert to the green object, it means that they can't see each other. Protons and electrons can't see each other, essentially. They're invisible to each other, where protons can see protons and electrons can see electrons and hate them intensely. So the basic idea is that one of those objects sits in its field and it gets hit by a force. A piece of electron force hits it. Alright? And it can do two of things. If this thing is already moving in this direction, well, then you're going to get a reflection. And the way it can have a direction that it already has acquired is by getting hit by more force from one side. So as each piece of force hits, if there's no force, if the electron is still, then it can collect a piece of energy from a direction. It'll stick. And if it doesn't get an opposing sticker from this side, if nothing happens coming from this side and another one hits here, it can collect 2, or it can collect 3, or collect 4. And then as it's traveling now, moving something less than the speed of light, because it's the same equation of mass. The force is very small and discrete, so it has to share its force with the mass of the object. So Sisyphus pushing a boulder moves a lot slower than Sisyphus when he's free. So it's no longer going the speed of light, the force, because it's pushing a piece of matter. And then the opposing force shows up. Well, then there's going to be a reflection. That is, this last little bit will fly off that way and this bit will reflect. And now this has only 3 things pushing it. And if another one comes in, then the same thing's going to happen, and then it's only have 2 pushing it. So it can only have motion in 1 of the 6 possible motion directions. So it can only be going forward. It can't be going backward at the same time. It can only go right. It can't be going left at the same time. It can't be going up and down at the same time. It can only be going up or down, or neither. So it can basically have motion in those 3 dimensions, depending on how it has acquired these bits of energy. So say if a piece of energy came at an angle like this, it would be additive because it's got a component in this direction, but it would obviously change all of this motion, would end up at this new angle. So it would just change the angle at which the velocity has now been acquired. And so it's a pretty simple dynamic. But the dynamic is that you either absorb force or you repel the force. Those are the only 2 choices. It either sticks and moves you, or it bounces off. Now, on the elemental level, that's all that's happening. There's no other option for acquiring the energy, and it's clearly you can't store an infinite amount of energy. because you're always, as you move faster and faster into the field, you're going to end up hitting more and more force because you're moving into a force. And obviously the faster you move into it, the more of it you're going to hit. And so that's automatically going to drag that velocity out of you. And that's basically what they see with electrons and protons. You can't shoot them to the moon. We can't make a beam of them, even in space, communicating between satellites or something. We can't send a beam of electrons because they just won't get there. And because they're going to get, they will, through drag, lose their velocity without the need of there being any atmosphere or any other substance to absorb them. I don't know if they've done any experiments with muons in space, so that would be the open question. Can they actually send a muon? Okay. Does it retain its momentum, its velocity? I don't know the answer to that one. Just for, I don't want to imply that I think muons are separate particles. I think they're just, when you do certain interactions, you're going to end up having two electrons pushing on each other. So you could have the situation where two electrons are repelling each other, but they're both pushed into each other, so they're both moving as one object. And they're both electrons, but they're not one. They're not some new particle. They're just two electrons. They can't connect to each other because they repel each other, and so they're just moving in the same direction, with some force behind them, gamma ray kind of force, very much force, and so they're moving very fast, but they really are just electrons. Since I started the subject, they say, they decay. And the fact is they don't decay. It's just that as they're traveling, they are going to, their energy, this energy that's pushing them, is slowly but surely going to be worn off by the friction with the elements they are plowing through and hitting the other objects. And every time they get near something, another electron, they're going to have their energy dissipated into those electrons, and so eventually they just stop. Okay, they don't need to decay. They just lose whatever they have left as energy, and that's it. Now they say they can detect this event, but I did a whole video on the muon detector experiments, and they're pretty bogus. In terms of this idea that somehow when a muon decays, it releases a photon in a scintillator. Okay, now that might be possible. Okay, that the last bit of energy ends up being something like the energy of an infrared photon, so it's possible it creates one. But I think anytime it has an interaction with an atom, it's frankly going to probably cause some sort of event similar to a photon. But no single atom ever produces a photon. All the atoms can do is produce the elements of a photon by producing electron motion. So as the electrons jiggle, they push force. Okay, but there needs to be more than one electron doing that at the same time to create the frequency and the polarization that ends up being a photon. So that's a much deeper subject, so we'll save that for some other time. Alright, so since the subject of friction slightly came up, the whole reason why there is this controversy is just these appearance issues. That the bullet appears, to have so much more energy than the gun recoil. But again, it's got to be appreciated that for every one atom the bullet has, the gun has 1,000 of them. And yes, it's going 1,000 times slower and blah blah. So it's really just about understanding that when something hits something, a surface, it's made up of a bunch of atoms. And those atoms have to, in some way, they all have to decide to move. You can't move something by just saying, object, here's one unit of energy now spread across all these atoms. It just doesn't work that way. They have to be spread through a process. They have to spread because one atom has to communicate with the other atoms. They can't all know, hey, the surface just got hit with something. They can't instantly know that. The only way they can know it is by exchanging information with each other in terms of all getting a jiggle in a direction. So they all get a little bit of pressure in a direction. And the simple argument is you can sort of understand that just like electricity, it can't move until it actually pushes the electron far enough, to jump to the next atom. It needs to have enough to push and cause the cascade. And if the energy isn't sufficient to cause enough of these atoms to be able to do that, then the energy is going to have to be reflected because it can't be absorbed by the electrons. They're basically saying, you can push me a little bit forward, but I'm going to move back before, you can do anything about it. And that's the time part. So when you hit something with something fast, you defeat some of that process, and you can bore a hole in something, like a head, with a bullet. Really because you're putting the energy in so quickly that the atoms don't get to communicate, nothing gets to communicate, and everything just gets blown to pieces in all kinds of directions. Now, the slower energy moves through a system is just like the rolling ball kind of example. The faster it can move through, the faster you can get the object moving, the less it's going to be connected to all the other atoms, so to speak. They won't be able to share the fact that an event is happening because you're just breaking all the contact with all the other electrons. So if you can hit something fast enough, the energy all keeps going very straight. But if you hit something slow, then you can sort of understand that all of the connections are real and there's a lot of energy going to be dissipated to all the other atoms in all these other directions. So slow motion, will cause a lot of the energy to be dissipated throughout the whole object. And obviously the end result you want is to have all these arrows going in all these different directions. They all have a component in the direction you want to move the object, and the object will eventually move in that direction. When all of the deciphering is finished, all the this way and this way cancel, and the only thing left is the this way. And so then the object moves. So obviously I can configure and show that a wrecking ball is better at knocking down a building because it dissipates its energy into a lot of objects and makes a large defect in a building, and therefore makes the building fall on itself through gravity. So it takes advantage of gravity by making defects large enough where gravity will do the rest of the work for it. And then bullets I can show where, they're very good at causing things to fracture and break and rip apart and spatter blood and do all kinds of things. But again, it's if you take the total number of atoms moved, it's always going to be decided whether you're moving them fast or whether you're moving them slow. It's always going to add up to the same amount of momentum, of real motion of matter. So if you tied the bullet to the recoiling gun, if you had a little string attached to the bullet and you fire it out of the gun, and they end up having a tug of war, the fact is you do have substantially the same amount of momentum going in both directions, and what will happen is one of them will not win. Even though this has 1,000 times more kinetic energy, it won't win because this is 1,000 times more weight, and it's going this way, and this is and so the resolution is going to have to be a bunch of motion that's neither in this way or this way, and just gets converted into a bunch of stuff like this, as most tug of wars would end in some sort of flipping, some kind of jarring of each other, and lots of vibrations, and maybe even some heat in the wire you're using to contain them. But you'll find it's all going somewhere. All the energy is somewhere. But what it's not going to be is obvious that the bullet has 1,000 times more energy, because it's just not going to win. And if I had some object in space and it absorbs these two things, okay, a bullet this way and a recoiling gun this way, it's not going to move this way dramatically. Not going to happen. Because it's the same amount of real energy, momentum. And there is no kinetic energy. There's just this appearance that small things going fast do more damage. And they do. They fracture surfaces. They have an advantage. They can break them. Okay? But breaking is not more energy. So this relates to the karate stuff that Paul is interested in. And the fact is, you have to increase the velocity of your impact on a board, because what you're trying to do, is cause enough fast displacement of the board. You're trying to cause this to happen, the bending to happen quickly, so the atoms don't have time to adjust, and they just start fracturing from each other. They start separating and breaking their magnetic bonds, their charge bonds, and their static, I guess would be a better word. So you're just breaking the molecular bonds between the wood, pieces of wood, and you're fracturing the fibers and all of that kind of stuff, because you're doing it quickly. You've applied the energy quickly, it's not being dissipated, and it's causing a bunch of stuff to displace dramatically, okay, and breaking the bonds that make the material strong. And you're just taking advantage that if you go fast, you can deform the surface, deform the object, and cause fracturing to start taking place, and the board will break. But if you apply even more pressure, but you apply it slowly, then there's lots of time for the energy to dissipate through all the little fibers and to cause the stress to move throughout the entire piece of wood, instead of the stress all being in one spot. So I mean, it's perfectly understandable, that as you increase the velocity, you can break something and use less energy to end up with the same outcome of a broken board, because you applied the energy more efficiently, in the sense that you didn't have to break the bonds in the entire piece of wood, you just had to break them in one section of the wood kind of argument. So it's probably enough of a video. So really, I mean, look, it's, I almost say it's almost kind of a trivial argument to make, that you shouldn't be deceived. The fact that applying energy quickly makes energy more effective at breaking things shouldn't be a big surprise. And it's no excuse for saying, oh, it's more energy, because it's just like any other modification you do to the energy. So applying quickly isn't much different than just applying it differently. The arrowhead versus the, say, square head. This will be more effective, and for discernible reasons, because you're going to create a huge amount of force over a tiny area, and you're now going to put them through a wedge that's even more effective at pushing energy, pushing stuff sideways instead of pushing it. This has to push everything forward, and if it pushes forward, that means it has to eventually push sideways, because the pressure builds up this way. It can't keep going that way, so it has to go this way. The energy has to make two motions. It has to go this way and then that way. And that's a lot less efficient than just pushing it sideways. So you can see there's obvious advantages, and for obvious reasons. But you don't say this has more energy merely because it's more effective. It doesn't have more energy. It just applies it more effectively for our purpose. And if our purpose is some other purpose, like compressing something, well, then we're not going to use that, and we're going to use this because we want to cause a compression. So, yeah, it's probably enough. It's just that, it isn't very complicated to understand that the speed is just taking advantage of a weakness in all of matter, that it can't communicate instantaneously. And so you can take out some of the soldiers really quickly, and the other soldiers don't know anything about it. But if you take them out slowly, then the other soldiers learn that there's soldiers missing and fill in the gaps. So it's that kind of a simple argument, that if you give it time to adjust, it will. And if you take advantage of the fact that you're not going to give it time to adjust, then you can plow through it. And that argument really, like I said, I think a 10-year-old can get some of that stuff. And it surprises me that the 30 to 60-year-olds can't, but whatever. Alright, so I think it's enough for the video. And so, till the next time and such, and we'll see where we go. I mean, it'd be nice if we could get Paul to actually engage, draw some pictures, explain why he thinks it works his way by actually refuting what I have diagrammed. So just explain where I made some gigantic mistake, in my drawing, illustrating of the dynamic. Let's see if he's brave enough to do that. Really state also that he has some evidence that, the energy lost in all of these inelastic collisions or absorptions, the ballistic pendulum, for example, that actually is somewhere. That the kinetic energy actually is recoverable because it exists as heat or something anyway. And that they don't demonstrate. So they just claim there's a bunch of heat and deformation. They don't show any of it. Alright, so probably enough. I'll declare it so. So till the next time and such.